All right, so this is the second half that I supposed to finish in the class, but I didn't finish. So this is on filtrations as well as inactivations. These are the two processes we are going to learn in these short videos. So what you learned in the previous slides that you first remove particulates by sedimentations, and everything that can't be removed by sedimentations you remove by coagulations. So once you finish those two processes, you pretty much remove most of the particulates. But there are small particles like bacteria, pathogens, they are not able to remove by this process because they are extremely small particles, less than 2 micron. And they also grow. So that's why it's very important to remove them by filtrations. So filtration process is basically a sand filter. You fill the entire tank like you see over here with a sand, and then we allow water to percolate through that process. So filtration means, and again I'm going to just draw this one. Imagine there is a column or cylinders, and you fill this with sand, fill with sand, and then you add water here and completely saturated, and then you collected water here. So this is effluent. Or sometimes people also inject from the bottoms, collect from the top to keep it saturated. So either way, the process is you have sand particles. As the contaminants move, they can stick around here. Okay, so this is sand, and they also have biofilm develop with time. So those biofilm will also capture more organic pollutants as well as the small bacteria or pathogens. So why filtration is important? Because it remove some pathogens or some remove biological microorganism, some of them, not all of them, and some of the dissolved pollutants. Okay, some of the dissolved organic pollutants that can be removed because of attachment to the biofilm. For instance, heavy metals can be also removed. So again, this process, the design is how much, what's the loading rate, how much amount of water you can inject, or what's the rate at which things are being filtered. So usually that's the Q divided by the area of the filter. So AF, that's why we call area of the filters. So that's a loading rate. VA, that's basically the flux that which water moves. That's the VA. Um, our loading rate, filtration rate is the Q over AF. Typically, the filter size is 100 meters square or square meters. So this is nearly 100 meters square. You need large surface area so that you can inject large amount of water. And the amount usually is 2 to 10 gallon per minute per square feet of the area. This you can turn into meter square or different units. So this is roughly the the design spec. Okay, you want to have within this range. You don't want to have higher surface more than 100 meters square because it takes lots of space. So you want to have a smaller, but if you go too small, you can't treat as much volume. And so now question is, sometimes you were asked to calculate filtration efficiency. The reason why filtration efficiency, what it means is that how much water you filter, what's the volume of water you filter based on the volume of water you injected. The question is, if you are filtering all of them, why it is not 100% efficient? Well, the reason is when you treat lots of water, it start getting clogged because you have these columns. You will clog a lot of things here. Now all the particles will get deposited. So once they deposit, it start clogging. The efficiency decreases. So you want to remove those particles. So what you do is you reverse the flow. You do back flushing. Okay, you do back flush so that you can disperse or remove all the sediments or small fine particles that deposited, and you remove those volume of water. That means that much of water we cannot treat because these are all being removed. And then you can inject again so that you can the cloggings are being removed. So that's why you have two process. You do backwash and then you rinse again. That way that there is no particulates coming out in the effluent. So because of that, you have to that amount of water that you do for backwash as rinse, you cannot inject them. You cannot use them for this process. So you did this one BF, and that's the amount of filter volume you injected, and the amount of volume you backwash minus amount of volume you rinse, divided by the amount of total volume that can be filtered. Um, so that's the efficiency. And now question is, what is the effective filtration rate? Is basically volume over time. So the way to calculate is the total amount of volume. So what you do is volume over basically the velocity is here, velocity. Um, so you just take that amount, volume of filtrations divided by area. That's basically is the velocity. Okay. Uh, Velocity, or the loading rate, filtration rate. So you take the effective filtration rate. So that means it's basically effective filtration rate divided by total time. Okay. So total time is TF plus TR, and then the effective filtration rate is the same as in terms of volume. You calculate that volume here, and then you calculate. This is just a number, okay? This is just the equations that you must remind yourselves to when it is asked for the examples. Normally, we don't ask any questions on this. Is just a concept to know. This is operation value people sometimes refer, nothing else. Filtration is not a big process here in this class because this is straightforward. I just want you to know so that in case this question come up in your FE exam, fundamental of engineering exam, you know that the number exists. What is more important is disinfections. Disinfection again is the most critical step because you do not, that's the last thing you do before you start distributing. And you do disinfection because there are pathogens that you can't remove by any other processes. This is the final check where you kill them. And the way to kill them is add some kind of disinfectants like bleach, Clorox, like you see over here. That's the whole process. And we watched this particular video in the class. You know that Legionella disease is something that spiked after the Flint water crisis. That's why you have to add more chlorine or more disinfectant to remove them. But just what we learned in that experience that you have to remove all the particulates and all the other stuffs before you add this chlorine. Otherwise, it will have unintended consequence or will not have the effect effective. So disinfection again is all about killing the pathogens, and there are two types of disinfection process. Number one is killing the pathogens directly during the treatment, and I think in that process where you want to design, where you want to add something very efficient or more potent disinfectant. The second step is the distribution system. The reason is when you have a treatment. Let's say this is the disinfection. This is treatment. Um, so this is coming from other treatment process, and then you distribute. Okay, so this is distribution system, like pipe coming all the way to home, and this is, let's say this is your home. Okay, this is home or end user. What you want is you even though you have clean water, these pipes can be contaminated because bacteria can grow in the pipes. So even you are treating the water, and when you are releasing them, those they might pick up those pathogens from the system, like what happens in that in Flint. So what you really want is you want to have some kind of disinfectants remaining when it leaves the system to account for that extra amount of pathogens in the distribution system. So that's why you want to add some kind of disinfect which can stay longer or can persist, because this pipe water can stay for many hours before it can be used. So that's why it's very important to have the disinfectant which is persistent as more opposed to potent, because persistent is important. If you're not using, let's say you use something very reactive disinfectant here, they will be destroyed within few minutes. So that means they will not survive, they will not stay effective until the entire distribution time. So that's why you have to think of what kind of disinfectant you wanted to use. So again, there are multiple types of disinfectants. Chlorine gas, hypochlorous acid. Chlorine gas is basically Cl2. Hypochlorous acid is HOCl. Okay, OCl. That's something that you have in your bleach. Okay, so that becomes OCl minus plus H plus. So that's why it's acidic. If you want acidic, it will dissolve all the corrosive products. And these are the two which are important. They are potent, so a lot of times people use those two, but they are not very effective when it comes to lifetime, because they will be used up very quickly. So that means it will not survive for a long time. That's why people use chloramine. Chloramine is basically chlorine gas with ammonia, and so when they react together, it forms a chloramine specific products. Okay, so this one we call actually combined chlorine. So it's called combined chlorine because it's used chlorine. And the reason this is used is because this is more persistent, which is useful for distribution system. Okay, and when they combine together, let's say chlorine plus NH3, it becomes let's say manganide NH2Cl plus HCl. That's what they found. And so this is what the disinfectant. Okay, if you add again one chlorine gone, so then it becomes NaCl2 um, plus HCl, and then it reacts with, and again this will become, you just basically release one chlorine HCl, NCl3 plus HCl. Okay, so nitrogen plus, so nitrogen in chlorine makes it stable. So that's why I call combined chlorine. Chloramine is less effective as oxidants like HOCl, but it can be, so that's why it's not used as a primary oxidant. They're usually used for secondary oxidant. This is secondary for the distribution system. Um, and then sometimes we use ozone and UV light. The difference between these two, because you store those chemicals, ozones can be produced at the site because it's very expensive, and also it's very reactive. You don't want to store them. So a lot of times ozone is produced at the site. And UV obviously doesn't require any chemical, it's just electromagnetic radiation, so you can produce anytime. So this is produced in situ or at the site. Okay. But what is more cheap is chlorine. So that's why a lot of time people use chlorine. There's just also HOCl and all that. Okay. So when it comes to design, you add the disinfectant. You have to add at certain rate based on how much stuffs you want to destroy, and then you have to mix properly because pathogens could be at different locations in the disinfectant. So usually you have a big mixing system. You had a disinfectant infectants added at certain rate. That's based on the amount or mass balance you can calculate. So we'll get to that. Um, One of the things that you have to remember is disinfection process can create other harmful organic chemicals like disinfection byproducts. Because when you think of chlorine and it adds with natural organic carbons, so NOM, which is basically organic carbon, okay, organic carbons, and it reacts with chlorine, it produces organic carbon with a chlorine bonded with the organic carbon, like TCM, all this thing given here. And these are actually carcinogen. They are extremely stable and they are highly contaminants. So you don't want to produce, you want to kill pathogens, but it not the cost of creating carcinogens. So that's why it's very important to understand how to minimize this production of disinfection byproduct. As you see, the reason for why it is being produced is NOM, natural organic matter. So the best solution is remove NOM. That's why you actually in fact have a filtration process like sand filter to remove the NOM before you use it. Okay, so that's why you need to remove by filtrations, and sometimes you use adsorption, basically because sand itself doesn't have much adsorption capacity. You use activated carbon, granular activated carbon. So the NOM is going to adsorb on this much effectively. So that's the process people use. So instead of using sand, you just use granular activated carbon. And so now that you know that disinfection rate is dN over dt times. So usually you know that disinfection before I always write dN by dt equal to minus k. That's a first order reaction time n. So I'm just putting star here. So what that means is number of bacteria or pathogens in a system. The rate of change of concentration of pathogens in the system is a function of the concentration of pathogen in the system times the rate constant. So before I always write this one. What I didn't write is this disinfection rate depends on the amount of disinfectant you add. So that's why the K star is actually some killing rates or coefficient of lethality times amount of disinfectant. So C is concentrations concentration of disinfectant. Well, you know that this is the process where you add disinfectant at certain rate, and then you have also a flow coming in. So that's the Q of this water that you have to inject, and the water coming out. So that's why when you add disinfectant, it becomes diluted. How much it diluted is exactly what's the even you are adding C here, it become diluted to certain value. So that's why you have to actually the concentration will be less, a lot less than that. So this is called coefficient of dilution to account for the dilution factor. So you can solve for either way. This is known based on the flow rate, how much disinfectant you are adding at what rates, and then this is the coefficient of lethality. That's basically kind of how quickly it can kill. That's empirically determined. But ultimately, you want to solve for this value. Okay. So let's solve an example. That's the last thing that we're supposed to solve in the class. So I'm going to solve it. So as you see here, I'm going to read it. Because of the purity of your groundwater source, a water utility only has to disinfect the water before delivery. The utility uses ozone as its primary disinfectants and treat 10 million gallon per day. So the flow rate here, Q, is 10 mgd. Okay. Um, the ozone is bubbled into the water as it passes sequentially through 4 chambers of disinfectant contact tank. So it says that you are doing at sequence. You have 4 different chambers. So you have 1 chamber, you have 2 chamber, you have 3 chamber, and 4 chamber. To make it more effective mixing, you have multiple chamber as opposed to 1B1. Um, each chamber tank is well mixed and hold 50,000 gallons of water. So the volume of that chamber is each of the chamber is 50,000 a gallon. Okay, um, and it is in the same ozone dose. So it's saying that you are adding ozone at same location, same amount of ozone for each one. Okay, that's ozone is added here. Um, And you say that, as discussed earlier in section 3, EPA requires that Giardia, which is the pathogens you want to remove, concentration be reduced to 1/1000th of initial concentration. So what you're saying is this n by n0 should be 1/1000. Okay, initial concentration, or refer as 3 log reductions. What is the minimum ozone concentration that must be used to achieve the required removal of Giardia? So you're asking what is the ozone amount. So ozone amount is C. You're asking what is the ozone amounts. And if you see, this is the equations. And the K value has the C. Okay, so if you calculate K, you'll be able to calculate C. So let's see, you have to do the mass balance. And the second question, the coefficient of specific lethality and coefficient of dilution of ozone inactivation of giardia under these conditions are 1.8 liter per milligrams and 1 respectively. So I also gave you the K value, this K and N. So the K is given 1.8 liter per milligram per minute, and N dilution is 1. That means there is no dilutions there. Okay, dilution factor. So if you do that one, that means dN by dt. If you actually plot the value K minus K Cn N, so its K is given. This is given. This is K, and so I'll write Kc N equal to 1 times N. Okay, so this is one. This is one constant. Okay, so that you can write K star. Okay. So let's do the mass balance. So mass balance, you have to think of one. Let's say you have a 1 CSTR or CMFR. So you add this one, it comes here. So this is the QN0, and it become QN1. Okay, that's written here. It's going up QN1, and then you have K star N1. So if you think of the the mass balance equation, you can write the formula of let's start with a very basic one. So what I am saying is a steady state, so that means it's 0 dN by dt of system. Let's write mass balance Q, everything coming in minus everything going out minus everything reacted. So volume time K star time N1. This is steady state, so this is 0. So this is steady state. Okay, so that means you can solve for N1. If you solve this one, if you take N1 common, it becomes, I'm just going to write Qn0 by Q plus V K star. If you divide Q in both sides, it will be N0 by 1 plus V by Q K star. And B is basically V by Q is the retention time. So N0 is the amount of time it's spent. So that's right, basically theta retention time K star. Okay. So now if you do the same thing for the second one, the second column, you just have to replace, you can write for this is first chamber. So if you write second chamber, you just have to replace N, now N, the effluent of the second chapter 2, the first one, you have to do the first one, what is input of the first one is N1 divided by 1 plus theta C K star. So if you substitute N1 equal to N0, then it becomes N0 divided by 1 plus theta C K star square. Okay, so here substitute this. Okay, N1 equal to N0. So what does that mean? If you have 4 chamber, the final effluent, which is N4, would be N0 divided by 1 plus theta C K star 4. Okay, so that's what you will receive. So that means you can now calculate the value based on this. And as you see, the removal, the final removal, N4, or another way to say is the final removal, N4 divided by N0 is 1 over 1000. This is given. This is the standards that you have to maintain. So N0 by N4 is given. So all you have to do is solve for K star. K star has the concentration term. So if I write this one, if I solve for, so I'm going to write here, K star is Kc. Okay, N equal to 1. So if you substitute that value here, you are just solving for C. So what I'm going to write the equation directly. It will be N0 by N4, 1 by 4, minus 1 by theta C K. Okay, so that's the one you are going to solve for it. All right, so I think that's all. We have everything. So this is the second half. I'm going to conclude that, and I hope you can solve all these examples looking at the textbook.